Welcome everybody. My name is Schmidt. I work here at the Department of Astronomy at Stockholm University, and I have arranged this together with Ariel and Serena and Brahman. You will experience something quite unique here. We have the 3 Nobel laureates. Saul Perlmutter just came in here. Schmidt, Adam Riess. I don't think we need to introduce these people anymore after this week. You were probably at the Nobel lectures, so you have heard something about the discovery of the acceleration of the universe, but this will be different. Because, as you heard at the Nobel lectures, these were not alone. There are actually 2 competing teams behind these guys, and they are here tonight. For example, Brian and Adam, they were running the High-z Supernova Search Team, where also I was a bit involved, and most of the people are here tonight, 20 plus people. Can you please rise up so people see who we are? That's only half of the story, because Saul Perlmutter's team, the Supernova Cosmology Project, they are also here. So please, SCP, rise up. Thank you. So most of these people will actually help tell the story of how they discovered the acceleration of the universe. And this will be moderated and coordinated by the Nobel laureates. So before we start that, I will just take this minute to thank the people that actually funded this and made it possible, so I have to read here. The Oscar Klein Center, Department of Physics at Stockholm University, the Alba Nova University Center, Royal Swedish Academy of Sciences through its Nobel Institute, and the Department of Astronomy. Thank you very much.
Okay, so this is the first panel discussion, which is the early history leading up to the formation of the 2 teams and then towards the discovery. And we'll start out with Nick Sunseth.
Thank you, Adam. An old astronomer in Saratoga once told me that you know you're getting old when the astrometrists begin to ask you for your plates. And going first on a panel like this is also another way of feeling really old. And I have to talk about the oldest part of the subject, is the quest for Q0, because ultimately what the teams really measured was the acceleration of the universe. Dark energy, we didn't really measure that. That's an interpretation. We measured supernovae were too faint, and the first order interpretation, a kinematical one, is Q0. And we also forget that the observational quantities that we use, magnitudes and so forth, it was very, very difficult back in the 1950s for astronomers to do cosmology, because they had no idea how to convert fluxes into, in cosmology, into actual things they could measure, like magnitudes. And there was one astronomer who hasn't been mentioned here, which I find really unfortunate, who was instrumental, and probably to me the greatest cosmologist of the 20th century, is Alan Sandage. Now, Alan Sandage was Hubble's, he wasn't his student, he was his helper. And Alan Sandage, when I knew him back in the 1980s, said there are really only 2 numbers to measure in astronomy, H0 and Q0. At the same time, he said there's lots of interesting astronomy to do along the way. And so, along the way, he discovered the main sequence of stars and globular clusters. He understood why giant stars became giants. He discovered, probably more than any other astronomer, in his quest for doing cosmology. He measured Q0. He actually brought Q0 down from a very large value to a value that's close today. But his other number that he wanted to measure was Q0. And around the 1960s, he wrote an incredible paper where he set out all the possible ways of measuring the deceleration of the universe. And he called these world models, which is interesting because that's the word that Friedman used in the Russian school of cosmology. Different world models that you would measure for the cosmologies. So in this particular paper, he set out a number of different ways of doing this, which is very unusual for astronomers. Usually we like to keep our technique secret until we actually publish the papers. In this case, Alan Sandage told us in this paper how to do various ways of measuring Q0. Well, he didn't talk about supernovae. Supernovae was done later by Alan Sandage and Gustav Tammann from Switzerland. And in the 1980s, they put together a supernova search project using photographic plates to search for supernovae that were far enough away to measure the deceleration of the universe. They used photographic plates. It turned out the photographic plates had flaws in them. And Bruno Leibengut, where he is, was very much a part of that. Hi, Bruno. And so that is the beginnings of all these projects. And I'm setting the stage such that we're now about 1984, 1985, and the Taman and Sandage project has now failed. And at this point, the two groups began to, we didn't form, but we began to think about the problem. And I'll leave the subject off at this point.
Thank you. The microphone to a man who needs no introduction. Bob Kirsch.
Yeah, where is the microphone? Oh, thank you. Honestly, I had no idea this was going to be actually had some content and a sequence and some logic. So there's just me. I'm ready for the first slide. Where's my assistant? You could be as Sandage was to Hubble. I wanted to take 1 minute to talk about the memory of someone. And that someone is Charlie Kowal, who died just in this last month, who really was in on the beginning of supernova cosmology. As you see, he has in his hands here the photographic plate that was the tool of astronomers that Nick was just referring to. This is in 1968. For many years, as Zwicky's heir, he, Charlie Kowal, did monthly searches early in the dark run for subsequent follow-up of supernovae, and he found many, including one even brighter than 2011 FE. Where are you, Richard? Which is supernova 1972e, the one that I used for my thesis. It's like the Paleolithic pan-stars. Next slide, please. And here is the Hubble diagram that he published in the Astronomical Journal. Good journal, you should publish stuff there. In 1968. He had distances which are good to about 30%, but he speculated that if you had better measurements, that the supernovae were good enough for 5 or 10% distances. And of course, that's what we've done. Charlie also said, and this is really quite interesting, we usually just clip out the plot from his paper, but if you read it, which is unusual, it says, it may even be possible to measure the second order term in the redshift magnitude relation when light curves become available for very distant supernovae. This is exactly what Nick was talking about when Sandage worked out in terms of magnitudes what would be the effects of various world models. He put it in that language, and what Charlie's saying is if you could find the distant supernovae, you could do that, and that was 40 years ago. Okay, next slide. So here's a modern version of the nearby diagram. It shows that this prophecy came true. Next slide. Here's the technological point I wanted to make, that it started with photographic plates, and of course the new thing was solid-state detectors. Here you see Bev Oak, who was my thesis advisor, with one of the world's largest charge-coupled device, a 0.24 megapixel camera, well, CCD. The group of people here is very talented, very hardworking, but there's nobody here who's a better physicist than Einstein, and nobody in any of these groups that was more creative than Zwicky. But the thing that we had was the technology which got developed in the 1980s and 90s, as shown in the next slide, which shows John Tonry looking at an array of CCDs as big as one of those photographic plates. Next slide. Now, of course, we're interested in supernovae because of the distance scale, but we're also interested in the fact that they make the chemical elements like calcium that's in your bones, like iron that's in your blood, like the oxygen you're breathing. Here's an early picture of some of the members of the High-z team. But you never get to see Mark Phillips in this picture because I think he took it. Well, anyway, next slide. The last thing I want to say is that I've always known that all the students I've had are way above average. I just wanted to wallow in the emotion of this for a second and just say that there are many, many people, including on both teams, who I've had the pleasure of working with closely as postdocs and students. Tom Matheson, who came to be a postdoc, Pilar Ruiz Lapuente, who worked on the other team, and then on our High-z team, Pete Chalice, who's been a staff member and really the spirit of the group in a lot of ways. Bruno Leibengut, we heard, worked on the early work and was a postdoc. Chris Smith, who's the director at CTIO. Brian Schmidt and Adam Riess, Peter Garnovich, a postdoc with me, and Saurabh Jha, who's recently done his PhD and was part of this project. Now I believe that since the universe is accelerating, that sooner or later we would have found out that it is accelerating. It couldn't have been done sooner because the technology was not right. It could have been done later, but luckily we had the efforts of these people and all the people on the SCP to work on this. So I think it would have been found sooner or later, but it's the hard work of the people in this room that made it happen earlier rather than later. Next slide. What's our motivation for this? Is it to improve technology? Is it to improve the national defense? Is it to make medical improvements? No. It's for the joy of finding out how the world works. And now, I want to give you a copy of this fine book, which you probably haven't spent any money to buy.
Thank you. Now we'll hear from Richard Muller.
One doesn't do science out of curiosity. If you're a curious person, you go to the library, you get facts much more rapidly there. You do it out of the sense of adventure. Our supernova project started in 1978, and it came about, it was made possible by 3 projects, which you may not know too much about. The first one you do know, cosmic microwave background radiation. That was a project for which we had found the cosine anisotropy. And the second one was radiocarbon dating with accelerators. That was a new method that's now become standard. Based on those 2 projects, we were given $150,000, that's $1 million kroner, to spend on any project we wanted. That's unheard of, and it's a challenge, and it's a responsibility, because that happens so rarely. You have to pick something you couldn't do otherwise. So I had been to a talk by Bob Wagner, got really intrigued with doing cosmology with supernovas. I talked to Louis Alvarez, and he said, hook up with Sterling Colgate, join his team. Sterling, it turned out, had just finished his project, so instead I hired Carl Pennypacker, and we got going on a project I called the Omega Project. We're going to measure the mass density of the universe. Well, you know, technically, but that's what we called it. The project was canceled 3 times in those early days. And just so you don't think that this is easy going, I thought I'd say something about that. The first time was when we had a new director of the physics division. I had that $150,000, the $1 million kroner. We also got money from the physics division. The physics division had to cut us out because our project was cosmology and it wasn't particle physics. So when the budget dropped, they were going to cut us. Dave Jackson, who you probably know, because he wrote that famous book on electromagnetism, was the person who said, sorry, Rich, we're going to have to cut your funding. A remarkable thing happened that same month. We came out, the Alvarezes had figured out what killed the dinosaurs. I and several of my colleagues at Berkeley had come up with a nemesis hypothesis, that there's a star orbiting the sun. And based on that, I had a great new graduate student who was going to do his PhD thesis on that. His name was Saul Perlmutter. And so based on that, Dave Jackson couldn't cut us. The second time we were cut was I'd gotten some money for the radiocarbon dating project, and that was going to be cut too because we weren't allowed. See, I was cheating a little bit and spending that money on supernovas, but I had learned the tricks of the game, and I realized there was a document that nobody ever read in which you put down the projects you're going to be doing next year, and I had included in the supernova project. So the radiocarbon dating supported the supernova project. The third time we were canceled was when we started the Center for Particle Astrophysics. And there, we had 3 projects. We had George Smoot, we had me and Bernard Satellite. Bernard was the director. One day, Bernard came to me and said, Rich, we're going to have to zero your project. And why? Well, there are all these problems you haven't solved. There may not be any supernovas at Z equals 0.5. You haven't demonstrated that. There's the K correction. You haven't figured out how to handle that yet. He went through this whole list. He said, I've consulted with the supernova experts, and they tell me your project has no chance of working. And so of the 3 projects, we're going to have to cut your project completely. Fortunately, there's enough money that we can give it to Bernard, to his own project, Bernard Satellites. Anyway, the unsung hero here is someone called Bob Kahn. I went and told Bob was up at the LBL, And I said that Bernard is cutting me completely, and he said, well, we will restore the funding that you lost from Bernard. Where are you going to get that from, Bob? He said, well, just cut Bernard's project here at LPL. So it all worked out just fine. And let me just wind up then with a general statement that when you have a chance to do a project that is new and different, it's your responsibility to do it. Tenure is not something that is an honor or a privilege, it's a responsibility. So we started this project, and it's an adventure. It is not like going to the library. You don't know if you can do the project. If you know that you can do the project, it's really not that interesting. So there are lots of problems that have to be solved along the way. On the way, it's like Columbus trying to discover America. You spend most of your time trying to get funding to do it. And it's really hard, and you lose the funding. So you're low on resources on a project you don't know that you can succeed at, and here you are doing it, and in the end, you have to suffer the attacks of the natives. So.
Thank you. And now we'll hear from Richard Ellis on early Viking history.
Okay, so since we're in Scandinavia, let's talk about the Danish UK survey. So as you've heard, CCDs, digital detectors, came on telescopes in the late 70s and early 80s. And not only were these high efficiency, but they enabled us to do look for distant supernovae for the very first time. So the story here is very interesting. Warwick Couch, where's Warwick? Who's on the SCP team, and I were in Durham in the north of England, and one day we got a phone call from Henning Jorgensen, who was the director of the Copenhagen Observatory, and the Danes had a telescope at ESO, the Danish 1.5 meter telescope, with a fabulous CCD, 500 pixels by 500 pixels. Now, what was our access to this fabulous instrument? It was that Warwick and I uniquely had a sample of about 70 southern distant clusters of galaxies. The field of view of these cameras was so small that a cluster of galaxies optimized the possibility of finding a supernova. So this was really a fabulous opportunity for us to at least begin this very interesting experiment. So we basically would go out to Chile every month. Because supernova don't hang around, so you have to observe all night and then stay up in the morning and reduce all the data and compare with the previous month. So we really learned that this is terribly exhausting. And we didn't know how many supernova we would find. The predicted rate per galaxy was uncertain to a factor of 5 or so. So, it could be that after 2 years surveying, we'd either find 4 distant supernovae or as many as 12. Well, in the end, we found 3 supernovae and 2 possible supernovae, and the one you see here is the one that we published in Nature in distant cluster AC118, which Warwick will remember for his thesis. And you can see that the light curve is kind of embarrassing. We discovered it after maximum light, but what the heck, this was the first distant supernovae, and so we sent it to Nature. Now, in order to follow up these supernovae, of course, one would need override time. So my role was to write and get permission to kick people off all the telescopes that the UK owned at the time. And so, this was quite a novelty to, somebody would come in and say, we found a supernova, Ellis orders you off the telescope so that measurements can be made of this supernova. And the letter that went out to all of the community who had observing time basically said, don't worry, he'll never find one. So this work got published in Nature, and it got rapturous reviews by a certain individual here. You can see it says, I admire the work very deeply. I think he still does. And basically, however, he says at the bottom that we should not get carried away. We should it's going to take very, very hard work to measure the deceleration of the universe. They are embarked on a difficult path, which we all hope will succeed, but we should all think very carefully before going down this road and doing this project. So I just thought I'd remind Bob of that. And Hubble, notice he already mentioned Hubble. So just to conclude, the amazing spectrum that we got of the first SCP supernova with the LDSS-2 instrument at a redshift of 0.458 was an exciting moment where Carl Pennypacker, who I think deserves a lot of credit for the infectious enthusiasm that he brought into all of us and inspired us to get involved in this activity in the early days. I'll never forget that phone call, Carl, where we phoned you. What I also won't forget is the thousands of phone calls from Saul Perlmutter, who must have spent his Nobel Prize on phone calls already. So Saul is the master of the telephone. When people go observing, there's usually 2 people to man the telescope and reduce the data, 1 person to handle the telephone, and he liaised with Saul. Saul would phone at the most inconvenient times, but it's his persistence that led to the success of this project.
Thank you very much, Richard, and now Carl Pennypacker.
Thank you, Adam. I think I want to maybe describe, I won't talk as fast, my wife won't believe it, but describe some of the background at Berkeley. I think Rich mentioned that there was an amazing entrepreneurial spirit there. And, we're not that far from Silicon Valley after all. And the idea that I think Louis Alvarez infected us with was that you could find a big problem, and if the technology was right for it, or getting almost right. I mean, it's never clear the technology is always right. You could assemble a team of smart people. You could work hard. You could resist the peer reviews. In fact, our first peer review proposal to NSF, the reviewer kindly said, "These guys remind me of a dog chasing a car." So, if we had taken the reviewers seriously, there'd be nothing. So, all young people there, damn the torpedoes, okay, that's one advice. It's very clear, that the peer community was not for us. We were physicists, we were astrophysicists, we weren't supernova people. So there was a lot of difficulty getting into the field, but we did things that nobody had done. Rich was the principal investigator. I helped lead the day-to-day operations of the nearby search. That started in '81. So again, young people, stay young. This is 30 years later from '81. Sad note. Nothing was quite ready technologically for the nearby search. But by '86, it was working quite well. We found 25 supernovae. It was the first really regular automated nearby supernova search. And at that point, we were eager to go further. Saul and I talked, said we have to do something special. And then we were blessed in '88 with the discovery of the Danish supernova, the Danish Durham AAO supernova. And Warwick happened to come to town in that time. And he said, "Look, we have a great telescope." In fact, I called the Danes, the wonderful people, and said, "Let's try to do something more." And they said, "It's impossible. You'll never get that to work." And Warwick realized the AAT was a large aperture telescope, 4 meters. We built special optics. Maybe Heidi will talk about it later. And so we developed something, a very large field of view, very sensitive instrument. That turned out to be, I think, the keystone to the whole project. Big field of view, big aperture telescope. And then so that led on then through the AAT days, which were, I think, we're quite successful in building the software and getting the team together and finding our methods. We transitioned, we probably had a few supernovae in our data. Heidi claims there was one there. We went to the INT in '92 and then found our first supernova rapidly after that, and then led to '94. Saul took over completely in '94 and has just done a superb job of management and doing great science. One other tip from Louis Alvarez. Louis would say that if your junk pile was not big enough, you weren't trying hard enough. And that, I think that, we'd go into something, we'd find out it wasn't working, we'd fix it. And I think thanks to to Rich's leadership and funding, able to pull funding out of the hat. He had prizes. My children have made a food out of his prizes, bought for by his prizes. Thank you, Rich. I think we were able to solve problems as we were going along. We'd peel the onion skin back and get it. And I think keeping resilient in the face of this is really the key. Thank you.
Thank you very this session, Mark Phillips, Chilean history, and more.
Yeah, you don't have to read this. This is just for me to remember what I'm supposed to say here. I wanted to start off sort of Chilean prehistory by talking a little bit about the Cerro del Roble supernova search, which Jose Massa led from 1979-1984. They discovered 50 supernovae using a Maksutov telescope that the Soviets had abandoned when they had to leave the country in 1973. And Jose was quite successful. He discovered among the supernovae they discovered were 1980N, which was in the nearby galaxy 4NXA, and 1983K, which happened to be the first supernova I ever wrote anything about, ever observed and wrote anything about. But actually, not the first one I observed. I think the first one was 80N. And then just very parenthetically remark that in 1980 and 81, near-IR photometry of 80N and 81B, and there's another one, 81B and 81D, excuse me, was carried out at Cerro Tololo, and although this wasn't the first near-IR light curves, they were among the best ever obtained to that point. Nick's already mentioned the Las Campanas supernova search that Bruno was involved in. 1986 was the watershed year for me because, first of all, my buddy Nick Sunsef arrived in Chile. Finally, I had a photometrist to work with. And then 86G appeared, which I got interested in because I was working on AGNs, and I wanted to know the distance to Centaurus A. Little did I know that, in fact, it wasn't so simple. When we reduced the data for 86G, I plotted it on graph paper. Remember what that was? And I put it on top of the David Branch's group's observations of 81B, and it was not the same. It declined faster. Then 87 came along. All hell broke loose when 1987A was discovered at Las Campanas. I had published 2 papers on supernovae and was the local expert. Mario Mui began his work as a research assistant 2 days after the supernova was discovered. He went to the mountain for a month. He was not allowed to come back. In 1989 and 93, we did a number of, we decided we had these wonderful CCDs with Nick and Mario. We obtained extensive observations of a number of supernovae, which in fact were the ones that in the end indicated to me that there might be some sort of a relationship between luminosity and decline rate. Thanks, Jason. And then in 1989, 1995 was really when all of this work blossomed into the Tololo supernova. Should mention that the germ of this survey was planted at the Santa Cruz workshop on supernovae in 1989. It was a talk that Bruno Leibenhut gave, which I understand was because you ceded him your position, where he showed the Hubble diagram. This is based on a lot of work done by him and Gustav Thomann and Alan Sandage. And I don't remember who, but it could well have been Bob, commented that, gosh, we could do a better job at this. And so we went back to Chile, and Mario had the idea of carrying out a supernova search. So we decided, let's do type 1As, because in fact, Jose had showed us that those were the ones you'd find in a photographic search. And one of the things I'd like to, other than the fact that this was really the first demonstration that supernovae could be used at the precisions that we're talking about today to determine distances, there's 2 more things I'd like to point out. One is, first of all, this supernova survey provided the data for Brian, much of the data for Brian's thesis. So we feel we contributed to Brian's nurturing as well. And secondly, this was, in fact, I believe, the first case where supernova search was done in a way where we could schedule the nights for the follow-up without having observed the supernovae. We would do this by taking the plates at a certain time during the month and then taking them 2 weeks later, and then we would ask for the time for following the supernova. So that's it.
Okay, I And we're going to transition to the next panel, which Brian.
All right. I think Professor Kirshner needs to catch an airplane. Is that correct?
Have to go.
Could you wave to everyone goodbye? For the next panel, we're going to be talking about the beginnings of projects, and Saul is going to be the heavy, but I'm going to arrange this right now. So we need Brian Boyle, Heidi Newberg, Ward Couch, and Alejandro Cocchiati. So Jason Spiramilio, the enforcer, will let you know when you have 1 minute left of your 3-minute allocation. We will clap you off the stage at 4 minutes.
Is that what we're doing? So begin with, do you want to begin with work? Sure. Okay. So we're going to have quick words from Ward Couch, and this session will kick off the beginnings of the project. So you'll be hearing from 3 beginning of the SCP, and then 1 from the beginning of the High-z team. Okay, Ward, go ahead.
Okay, so there's a very strong connection here between Berkeley and Australia, which we're very proud of. And I just want to say a few words about this. How did this come about? Well, Mark's already mentioned Supernova 1987A, and that created a lot of activity in Australia, particularly at the Anglo-Australian Observatory, where I was working at the time. And of course, many of us at the Observatory and also another institution in Australia went to many conferences that were held in the year or two after that. And in particular, one was held at George Mason University, I think late in 1987, and that's where I first met Carl Pennypacker. And we got talking, and he was very interested. He'd heard about the work that Richard Ellis and I have been doing with the Danish group, and was very interested in this distance search. And then, of course, we met again in Australia when we had another Supernova 1987A meeting, I think in 1988. And really that was the time when we really got serious about forming a collaboration between myself and Brian Boyle in Australia and the Berkeley group, including Saul and Rich. And of course, soon to arrive was Heidi, who was a student who was set loose on this wonderful project to use the AAT and the F1 Thompson camera to actually start our first distance search, which then morphed into what then became known as the SCP. So I don't want to steal Heidi's thunder or even Carl's, because this was Heidi's PhD project, and I'll let her tell you about that wonderful but rather unlucky, I think, series of observing seasons on the AAT, where we really had terrible weather and did not get a lot achieved. Over to you, Heidi. Thank you.
So in 1988, I was a young graduate student at Berkeley. I had just the year before learned what a supernova was. And I actually had no idea it was going to end in a ball gown and heels, I'll tell you when we started. So I was working on the nearby supernova search, and one day Carl Pennypacker, as he was running out the door to go catch an airplane, said, "Hey, I'm building an F1 camera in Australia, and there are a few things that the engineer upstairs is working on, and I need you to go and help the engineer because I got to leave now, and he has some questions, I don't know." And he left. And that is how I got started on what became the Supernova Cosmology Project. Was going to help the engineer. Apparently one of the jobs of being a physicist is to communicate, ask the engineer, what do you need? And he'd tell me, and I'd go back and I'd call down to the AT and say, well, this is what he needs, and I went back and forth. And in the period of time that I was a graduate student, we were trying to find the deceleration parameter of the universe. Right? And you have to imagine what it was like then. At that time, people were still fighting about whether the Hubble constant was 50 or 100. Right? So that means is the age of the universe 6 or 12 billion years old. And the stars in globular clusters were 15 to 20 billion years old. So it was a kind of a time in cosmology where we really didn't have any good answers, right? The whole picture didn't work. And it was a really great thing as a graduate student. You go to a cocktail party no one could ever be. You know, what do you do? Oh, I'm measuring the mass of the universe. Right? Is what I was doing for my PhD thesis. At that time, one of the key things is, I think several people have talked about, the CCD cameras had just come into common use in astronomy. And we were starting to be able to put enough pixels on the sky to do surveys. What comes with that is a lot of software, right? So there was a big shift, and this is something that I discussed actually. Saul Perlmutter is the person who taught me how to do astronomical analysis. But we're in a transition between astronomers who were just poring over plates with, you know, eyeglasses and scanners and looking at every little pixel, even the beginning CCD camera images. People would adjust them all by hand, and they'd measure everything by hand, and they were very involved with the data. But once you have these CCD cameras and they're bringing in tons of data and it's going on your computer, you have to shift over to algorithms that allow you to process the data almost to the end without human intervention. And so that was a huge paradigm shift in astronomy, to go from, you know, astronomers that are very involved in every pixel to being able to do it in an automated way. What more do I say? So I actually worked just as hard as all these graduate students who came after me. I went down to Australia. I learned to drive on the left-hand side of the road. I went out to the observatory. I did not hit a kangaroo the entire, but I did get lost in the outback with one of the Greek postdocs who was just learning to drive, and that's another story for another time. But we went to the telescope. We watched a lot of cricket. We had really a lot of poor nights, and what we learned at the end of that is that, you know, it's just, we learned a lot about how to look for supernovae. I mean, we learned you had to take the previous images very close to the later ones, because otherwise you would get active galactic nuclei that would come in and take over your images. We learned we really needed higher resolution than we could get at the AAT. We learned how to you know, that we needed both weather for both sets of images. We learned a whole lot. Is there someone with slides here? Okay. At one point, I remember I worked with Gerson Goldhaber, and he actually pulled this image out of our data from the Anglo-Australian telescope, and he said, "Heidi, I found it. This is what we're looking for. It's omega naught." But then I took this piece of paper, which he had signed. Actually, I don't have the signed version up here. And I took it into my advisor, Rich Muller, and he told me, "Oh no, you've got it wrong." And so, with this survey, in the years that I worked on it, we actually did not find a single confirmed supernova, but it kind of set the groundwork for what came later.
So next we have Brian Boyle, who will pick up the story.
Well, thanks very much, Heidi. I was privileged to be invited onto this wonderful team when they were observing on the Anglo-Australian telescope. I was a postdoc at the Anglo-Australian Observatory, and like Heidi and Warwick will attest, we went through many nights. I then moved to the University of Cambridge, and I distinctly remember one day being phoned up by Carl Pennypacker saying that he had a 2000 by 2000 CCD chip, but couldn't find any telescope to put it on. And of course, I immediately, not having learned my lesson from working with this crowd in the AAT, I immediately leapt at the chance and said, well, I know there's a telescope in La Palma called the Isaac Newton telescope that's actually looking for a wide field. And with Carl and Saul's usual enthusiasm, they were out there like a flash.
And we actually had that CCD initially on the telescope within a couple of months. It then probably blew up and had to go back. And in fact, it came back as a completely different chip. It was a Loral chip to begin with. It came back as a Ford chip. But now we had a CCD on a telescope that was 2000 by 2000, very nicely sampled images, 0.33 of an arc second. As you've seen, this team actually had cut their teeth on doing all the analysis. They'd got the actual systemized way of doing surveys right on things like the AAT, and everything was set to discover lots and lots of supernovae, apart from the weather. And the weather on the INT, believe you me, in December is not the best. And I think it is also a tribute, I think, to this team that, of course, the first supernova was found with the INT. 1992 BI was the first supernova found with the INT, with, I think, what was known as the Pennypacker camera. Actually, it was such a joy for the engineers to work with the Pennypacker camera that I used to think that Carl's Christian name had become something quite different. It was usually an expletive, you know, it's that Pennypacker camera. But we discovered the first supernova there, and then went on with the INT to discover the next 6 and give the INT I think, a real whole new lease of life. Technology was really important, and it wasn't just the CCDs increasing by a factor of 4. I believe it was only 1998 when the total amount of traffic on the internet exceeded Saul's phone line in terms of data flow. We even had modems out there at the time. Remember that modem at the INT? And again, Saul easily beat the amount of information over the modem on his phone call. We had wonderful engineers to support us. You know, scientists made dreams, but engineers make them happen, particularly with the technology we had in place. And the other thing that I've learned, I think, from both teams is diversity is a fantastic thing in team, diversity of thought. And the other thing, my greatest regret, is not taking more pictures. The worst thing about it all, I don't have a picture with Gerson. I mean, Gerson was one of the people that Gerson Goldhaber, who's no longer with us, is one of the people I found the most inspiring when I went over to Berkeley, in terms of his absolute commitment to believing that this project would deliver something amazing. Indeed, I remember spending Halloween with Gerson and Judy, and a conversation that went something like this, although memory is a very fallible thing. Gerson was waxing lyrical. He said, "You know, Brian, this can win the Nobel Prize." And to which I said, "No, Gerson, it's not going to win the Nobel Prize, but just shows you how much I know." So thanks for listening.
Now we'll switch to the. Ooh. Hold this. We'll switch to the early stages of the other team, the High-z team, and Alejandro Plotliadi will speak, assuming that the microphone still works. Okay, use this one.
Seems
what was the one up by the end?
Okay. Well, this is a short story about Brian Schmidt. And when I was hired as a postdoctoral fellow at CTIO back in late 1995. I arrived there and was invited by Brian to join the High-z Supernova Search Team. And I said yes, but I thought it was kind of boring, you know, measuring type 1a supernovae that are all the same. I was more interested in supernovae that were weird. But, well, one day I was starting to work for a night with him, and, you know, Brian has just arrived. He had taken a plane to go from Australia to New Zealand, then from New Zealand to southern Argentina, then from southern Argentina to Buenos Aires, then from Buenos Aires to Santiago, then from Santiago to La Serena, taken a shower, we had lunch, then spent the whole of the afternoon and evening preparing for the night. And I just wanted him to go to sleep, because we knew how to take images and prepare the images, but we needed him with a fresh mind to use the software that he himself had prepared. So, but I couldn't get him to go to sleep. He was happily hacking code and trying things there. So I asked him, Brian, what keeps you going? What's your fuel? And he said, you know, I think it should be the birthright of any postdoctoral fellow to work at least once in his life on a project that has the potential to become a Nobel Prize kind of thing. And I said, Brian, do you think you are going to get the Nobel Prize for telling where Q naught is 0.123 or 0.321? I said, wow, but what if we find something weird, like Q naught less than 0, or a cosmological constant? I said, oops. Well, there are some people that think there might be like that, the universe. Well, you know, the one thing that I want to bring here is not just that made me take the High-z Supernova search work more seriously, but the spark that I saw in Brian's eyes at that moment. I had seen that spark in many of you, I guess, in a young graduate student named Adam Riess too, many times. And it is a deep emotion that I feel when I see that spark in coming students and even fellows of the older generation. And I would like to celebrate that spark because it is by that, I mean, the union of all those sparks that we make, I mean, we lighten up this, the path of this mutual enterprise that we call science. So, this is it.
So, for our next panel, we're going to be talking about the first discoveries and running the searches. And so I need to have Rob Knopp, Peter Nugent, Chris Smith, and Bruno Leibengut.
Peter.
All right. So first up, Peter Nugent.
Okay, so I wanted to tell a story about how hard it was to do this work. I looked at my passport, my old passport, and I noticed that there were 13 trips down to Chile in a 4-year period. And as Alejandro just pointed out, traveling down there, you would get very jet lagged. Back then I hated flying, so I never slept. And you'd immediately go up to the mountain and you'd start observing. And the data, getting it back then, was horribly slow. It was about a 56K baud modem coming out of the observatory to send all of this data back up there. And it was painful, and you would have to then package everything in tapes and you'd take that back. Well, Rob Knopp and I got sick and tired of this, and we decided that, you know what, we needed to bring the processing power down to La Serena with us. And so we bundled up a whole bunch of laptops, a whole bunch of things which they don't even make anymore called jazz drives as our hard drives. And I remember getting to La Serena and then going on up to the mountain and seeing Brian Schmidt, because you got to remember the other team was observing the opposite nights we were. We'd be on 2 nights, they'd be on 2 nights. A month later, they'd be on 2 nights, we'd be on 2 nights. And so we were constantly there seeing each other. And Brian sees us come in with all this electronics, and he just looks, and of course he's been on one of these mad coding tears, and his eyes are bloodshot, and he's looking at me and he's like, I mean, he didn't say this, but you could see it in his eyes, you bastards, if I had that much. Okay? He would have been done long ago with this. So, we observe all night, we pack up the stuff, and I'm driving down in the morning to go to the cafeteria. And of course, you're in these Volkswagens. Now, anybody who was at CTIO back in those days remembers these Beetles. By definition, these Beetles had to have been the first Beetles ever made in South America, and as a minimum requirement for being placed on the mountain, I believe they had to have 200,000 miles on them at the time. I was coming down off the mountain in a very, very sleep-deprived state, and the brakes went on the car. Now, if you've been up on the mountain coming down very rapidly with no brakes, you realize you're in a lot of trouble. And the only thing I could think of to do was pop the Volkswagen up on this sort of wall that ran down by where the cafeteria was in the dorm rooms. And so I popped it up there, and the car's rolling along, and then it flips over, and it stops before it goes off the edge. And I was like, thank you. I don't remember anything else other than the guys coming out of the cafeteria. Somebody pulled me out of the car, and the Volkswagen was flipped up. They tested it out. They said, here are the keys. The brakes work just fine. I said, screw you, I'm walking. 1 year ago, I am sitting at dinner with Brian, and he said, do you remember that time you almost killed me at CTIO? I said, no. What was I doing? And he said, you were driving this Volkswagen down, and I was coming out with my laundry headed over. And all I see is Peter Nugent, his eyes. And he said, the only thing that was sticking in my head is first they bring their damn computers that are going to beat us to the punch, and now he's going to kill me. It was very nice to learn that I didn't kill Brian, and that he was the first one to pull me out of the car. So.
Chris or
You'll be next one.
well, that's tough one to follow. But
Chris Smith from CTI.
so I was going to comment on the process, Brian's process, rather organized process of bringing his software down as opposed to bringing computers down. So of course that involved actually installing the newest version that he had been working on in a sleep-deprived state over on the plane on the way to Tooele. And so usually we finally convinced him to arrive a day or two early. So we could, those of us down in La Serena could spend those 2 days tearing our hair out trying to install the software on our own computers instead of bringing the computers with us. But usually we got it working about after the second night of observing, we had it working. And we were fortunate enough, both teams were fortunate enough to, or smart enough, to come to Chile. And one of the comments I wanted to make was, first of all, one of the keys to this discovery are the facilities in Chile at CTIO and in ESO. And because of the incredibly clear skies we have. You heard a little bit about the weather in Australia, a little bit about weather at other observatories, but our observatories in Chile are really impressive in that when you go there, you're sleep deprived because you're always observing, because especially in the periods which we usually used in December, January, you're almost guaranteed time on the telescope. And the other actual comment I wanted to add was the recognition of the unsung heroes. We hear a lot about the scientists who are here and the scientists, the postdocs and the students who contributed these results, these amazing results we stumbled upon in our efforts. But just a comment to the infrastructure that's required to achieve these results from the telescope operators, who I'm sure had a lot of fun entertaining these two teams on alternate nights and watching the differences between the two teams. I know that there were a lot of jokes on the mountain about the differences between the two teams. And also the rest of the teams, the engineers who built the camera, the prime focus camera. Dr. Alistair Walker was a project scientist and a very capable engineer, Andres Montanet. But also everybody from the engineers to the technicians and the cooks who kept us fed. We always had competitions between the different observatories in Chile, whose food was best. And during this period, I think we were lucky enough to be feeding both teams the best food in Chile at the time.
Rob Knopf.
I think that it's already been mentioned that a fair amount of credit for the ability to discover the number of supernovae we found goes to Moore's law. If you could just put up the next slide. This is from 2001, but the idea is the same. This is a small piece of one CCD, and you have all of these little pieces of junk all over it, and you have to find the supernova in them. And as Heidi was saying, you don't go and look at all of them, unless you're Peter. So we did a search at the Keck telescope once, looking for supernova at redshift greater than 1, and here we are at the telescope, and Peter says, oh, I'm going to blink the images. And we're like, yeah. So he starts blinking. What does he find on the first thing? A supernova. It was a redshift of 0.1. Anyway, so if you're Peter, stuff like that, I mean, you run over Bruno, all kinds of crazy stuff happens if you're Peter. But of course, we have to do all this with the computers, and we couldn't have done it. In fact, the computers had to keep getting better because the chips kept getting bigger as well. a fair amount of stress hit us when we recognized that this wonderful new thing called the BTC, the Big Throughput Camera, which was John Tonry's 4-chip camera. We were worried about this, one, for the computer time, and that's why we showed up at Chile with a whole bunch of laptops to do the preliminary data analysis, and two, the internet bandwidth was not going to be able to get all the data back to Berkeley as we had traditionally done. So we did the preliminary analysis down there, and then we did a compression so that it would compress better. The data compresses better when it's flat field, just a tip, and send it on up to Berkeley. Peter was mentioning bringing these laptops down. I think when I went down, I had 2 laptops and a tape drive in addition to a jazz drive in my backpack. And I hate to think in what cell I would be at Guantanamo Bay today if I tried to carry that kind of stuff on an airplane. But fortunately, this was back in the 1990s, so we got away with it. So Moore's law was very important in terms of, and as time went by, internet bandwidth got a little better. Chris Smith may remember a nearby search where our bandwidth was FedExing a hard drive back and forth between Arizona and Berkeley. So we've done all these tricks. But in the end, the fact that the computers were getting better every 18 months, the computers have doubled in speed, allowed us to keep up with the rate at which we were finding these supernovae. And of course, you look now at things like SNLS and some of these other surveys that have gone by, and they put huge numbers of supernovae. And I'm just thinking, why didn't we have all those back then? It would have made it so much easier.
One small correction. I know you know the answer. You're just thinking. Tony Tyson. And
I
Bernstein
apologize. Yes, Tony Tyson is what I meant.
Bruno.
So this is quite typical. Jason signed me up for this talk. I didn't actually do this.
Look at your name, Bruno.
Right. I wanted to tell you a little bit about the careful planning that we had in '94 when we set out to do this project. Brian had us all sign up to do this, and in '94 we all wrote a proposal in September, October, handed in at the beginning of October. There was the BTC, the CTIO time. There was ESO time. I think Apache Point, you guys had applied for time with the 3 meter for the spectroscopic fallout. There was the MMT time lined up. And so it turns out we all got the time. And in '95, when we started to do this, I got the search dates from the CTIO people, and the search dates were February and March. Now it turns out the semester at ESO starts in April. So I had time in April, May, and June, which is pretty useless for supernovae that you find in February and March. And so it was a little bit of a weird situation. Now it turns out the good luck is, and I will remember that forever, new moon, as Saul explained to us, new moon is important. You want to find a supernova before the new moon, and then you want to follow them up right after new moon. Well, it turns out in '95, new moon was on the 31st of March. So the last search night was on the 30th of March. The weather that year wasn't also good on CTIO. The last search night was on the 30th. I said we had no candidate at that point. We had nothing. And I was brave enough to go down because I had the ESO time. I thought I'd just spend some time with the CTIO people searching. We were clouded out the second half of the night, so we walked away with one candidate, C14. I even tried to install your software at ESO. It worked. So we had a great instrument which allowed us to take an image as well as a spectrum, and it turns out the image showed the supernova. We had slightly better seeing, we had a better pixel size as well. So there was a supernova, and we took a spectrum. Actually, we took 2 spectra, one with orthogonal slit positions, and it took me 2 months to reduce the spectrum. I never forget how envious I was of Alex, who produced these wonderful spectra with a 10-meter telescope, and with a 4-meter telescope, you just bang your head. And so it took me 2 months to reduce the spectrum. I didn't get the supernova until Mark Phillips said, why don't you subtract the galaxy? Now, I had subtracted the galaxy before, but it didn't work, so I had to do something slightly different to work out. Now, one last thing about ESO, once the VLT got around, we were very glad to compete with Keck. We got a lot of time on the VLT. Everybody got a lot of time. Chris Littman is probably the best observer with the VLT ever. He did that. There was one occasion I wanted to tell you on the 3.6 meter that was. I tried to do spectra of this supernovae. and I get a phone call from Saul. And Saul says, "Oh, you have to observe that supernova." And I said, "Saul, this is not your night." And he kept on talking. And I finally said, "Look, Chris is on tomorrow night, you know." And Saul says, "What date is it?" So we worked that out. I didn't observe it. Chris got the time. One last thing. At ESO, we did invest over the last 10 years, and I know this is true for the other observatories as well, but we allocated 360 nights to supernovae. This is all the different programs. This is also nearby programs. But we allocated 369 nights with our telescope for supernovae over the last 10 years to follow this up. And so it's been a big investment, it's been a big adventure, it's been great fun. Thank you.
Okay, we're going to start the next panel. We can get Alex Filipenko, Isabel Hook, Chris Lidman, Ron Gilliland, Saurabh Jha, and Alex Kim. Okay, Alex, why don't you start since there's no more seats? Okay, go ahead, Isabel.
Okay, so this is on. I think this session is going to be more about the follow-up.
On the bottom. On the bottom is a switch.
Okay, thank you. Okay, so I'll just tell you a bit about how I joined the project and what I was involved in. And so I came from having done my PhD in Cambridge in the UK with Mike Irwin and Richard McMahon, who are also members of our Supernova Cosmology Project, but unfortunately aren't here today. And I moved to Berkeley in 1994 and was supposed to be working on another project at the astronomy department, but Richard and Mike introduced me to Saul and Carl Pennypacker, and they were so welcoming and such an exciting project they were working on that I ended up actually spending most of my time working with them. And one of the first things that they asked me to do was to go to Hawaii to use the Keck telescope with Alex Filipenko, actually, who's just there. So I said, well, you know, Hawaii, do I really have to? But, it's one of those hardships of astronomy, so someone has to do it, yeah, exactly. So I went, and of course, what a fantastic experience it is for someone coming straight from graduate school into working on this sort of project, a really exciting project with Alex being one of the known experts in supernova spectroscopy, so that was a great experience, and to use one of the biggest telescopes in the world, and indeed still is one of the biggest telescopes in the world. And so when we were going on these early runs with the Keck telescope, we actually had to observe from the summit, which you don't have to do anymore. They've now moved the control room to a very nice sea level offices. But at that time, we used to have to go up to the telescope, and it's 14,000 feet. That's 4,200 meters. So it really affects you, the altitude, and you can feel you get headaches, and you need to drink a lot of water to stay hydrated. It's a strange experience and environment up there. And what I'd like to do is show one object that we observed, which was, so we're now looking at a spectrum of a supernova. This was a supernova candidate that we called AGN2. And the reason it was called AGN stands for Active Galactic Nucleus. And this is because from the images that you've seen now, some of them, it's not clear what you're looking at. You see a bright blob on a galaxy. And in this particular case, the part of the galaxy that had got brighter was very close to the centre of the galaxy. So we didn't know whether it was the nucleus that was active and had got brighter, or whether it was a supernova that had happened to go off near the centre of the galaxy. And it's the spectrum that tells you what it is we're looking at. And it turned out that this was a supernova, and it's a fantastic one of the clearest ones we've ever got, probably. Actually, could you just go back to the... I think Chris is going to show that slide. So what we're looking at here, the narrow lines here are from the galaxy, the host galaxy. Okay, And the broad wiggly features are from the supernova. So what we're looking at now, this is supernova light that's bright enough to see the supernova features right from the beginning with very little analysis, and the redshift perfectly matched the redshift of the host galaxy. So then we knew we were doing something right at this point. But I'll hand it over.
So Chris Lidman.
Can you go back to the previous slide? So this is the same supernova that Isabel just showed, 94 AN, also known as AGN2, and 9462, and various other names. And it's, as Isabel mentioned, a very clear example of a Type 1a supernova. In the bottom graph there you see a match with a nearby supernova at 92A plus 6 days. Now, it wasn't always like this. If you go to the first slide, which appears to be out of focus for some reason. This is 1988 U. It was observed with a 4-meter class telescope, in fact the AAT. And it's the same supernova that was mentioned a little earlier by Richard Ellis, discovered with the Danish telescope through a lot of very hard work. And you see that the signal to noise is quite low, and it was caught also well after maximum light, 17 days after maximum light. So the comparison between the supernova data, which is the solid lines, and the dotted lines, which is the best match, is not particularly good. And so between that in 1988 and then 1994, the next slide please, you see the difference, and this difference is largely due to technology, and also to the method in finding these supernova, bracketing the new moon. And in particular, this supernova was observed with the Keck telescope, so a 10-meter telescope versus a 4-meter telescope. So it highlights the importance that technology has had in making significant progress. Thank you.
So go ahead and advance the slide there. Just to remind you of what the Kecks look like. Fantastic place. And yeah, Isabel, someone has to go to Hawaii and do the dirty work, right? In the next slide, you can see a Keck spectrum. And this really was gorgeous to look at compared to some of the spectra that our colleagues were getting on smaller telescopes. So the Kecks were fantastic. Initially, there were problems with the CCDs. There was a lot of electronics noise, and so we didn't get such good spectra. And I was complaining to Bob Kirshner a couple of times that the Kecks aren't that great yet because of the various noise things in the CCD. And he said, oh, well, you guys will fix it, and then you'll blow everyone out of the water. And this is an example of the kind of spectrum we got. But I remember that it was really tough. We'd get these charts from Saul and his collaborators sometimes at the last minute. We'd be there, twilight's in an hour, guys, get us the charts, get us the objects, Saul, and of course they were working very hard in Chile. It was very difficult for them too. But we would then get the spectra, and I remember Saul had this transparency where he had a Type 1a supernova at various redshifts, and we'd sit there looking at the screen of the partially reduced spectrum, trying to figure out whether this really was a Type 1a or not. And I don't know if you still have that transparency, Saul, but it was, it should be in a museum someday, because we classified the spectra on the fly in this manner. And it was hard, as Isabel says. We were up on the summit at the time, and it was hard to think. It was hard to work, but it was also very, very exciting because we knew that we were pushing the frontiers. So that was a really wonderful aspect of the work. And I particularly like spectroscopy and supernovae, so I enjoyed being involved in the CAP work for both teams, actually. If you could just advance to the next slide, I just wanted to say two more things, and that is that for me personally, it was an enormous thrill at the February Dark Matter meeting in Los Angeles to present, in this case, the High-z Supernova Search Team results. You can see the Hubble diagram that we had based on the Tololo survey and also the CFA follow-up work at low redshifts, and then the 10 best observed supernovae up there. And you can see our best fit. It was just incredible, because these were all spectroscopically confirmed Type 1As, well observed with colors measured so that extinctions had been taken into account, and without any assumptions, without assuming a flat universe or anything like that.
we came up with this weird result, and it just blew us away. And that was just such an exciting moment when Adam showed me the results of his analysis in December of '97. In the next and final slide, you can see our omega lambda, omega matter contour plots. And again, sort of at the 99.7% confidence level, there it was. There was the result without using a flat universe, with reddening corrections made, systematic effects like evolution at least partially taken into account. And when Adam first showed me the photometry, I thought, gee, Adam, didn't they teach you how to do photometry at Harvard? I mean, this can't be right. But with additional work and Brian Schmidt checking the result, turned out it was right, and I couldn't have imagined being involved in anything more exciting. Thank you.
So in 1991, I was a bright-eyed and bushy-tailed graduate student arriving in Berkeley, having no idea what kind of science I wanted to do. And then I looked through this little guide and I saw Rich Muller. He's weighing the universe. So I said, I'm going to sign up for that. That sounds fun. So I started there. I spent a few months there, and it slowly dawned on me that they hadn't found a single supernova. Nobody believed that they would even find a supernova. And then at that point, it was Rich and Carl who were leading the group. But then, due to certain reasons, Saul became the head of the group. So things looked pretty depressing and bleak. No offense, Saul. But Heidi was just finishing her thesis, and she said, don't worry, you'll get a thesis out of this at least. But instead I got a trip to Stockholm. So being a graduate student there, I did many things. I worked on search software, and just to mention a few names of people who are not going to be standing up here, Matthew Kim and Ivan Small, we worked hard on that search software. I also worked on light curve fitting with Don Groom, who's sitting up here. I also wrote the code, the first code, for doing a cosmological fit, omega mass, omega lambda. And unfortunately, that code had some bug in it in which we were finding a non-zero cosmological constant. We were trying to figure that bug out for a while. And after that, I guess Seb Fabreau and Robert Quimby worked on the cosmological fitters as well. But oh yes, and then I also worked on some light curve shape stuff, but that's kind of boring. I was told like 2 hours before this meeting that I was going to give a presentation on K corrections. But this is probably one of the most boring things I did in graduate school. But I think one thing that I want to mention from K corrections is that even though the two groups had a great rivalry, we also worked very closely together. And I should acknowledge that basically all the code I wrote for K corrections was based on Bruno's code that he gave me when I was this bright-eyed, bushy-tailed graduate student. And I should also mention that a little birdie told me that the referee of this paper, the K correction paper, was actually, where is he? It was Brian. I don't know if this is completely true, but I got an email from Brian saying, the referee asked me to, check these numbers, and they're wrong. And of course, it was Brian that was wrong, so. All right, no fighting. No, this is all very friendly, right? But K corrections are technical, they're irritating, and they're scary because there's certain issues about astronomy and magnitudes and fluxes, and astronomers don't really use energy units. They don't use NKS units, they just kind of pick numbers, and those are distances based on these numbers. So there's a kind of complicated thing transferred between magnitudes and actually coming up with physical units. And the calculation is non-trivial, and for 4 years after the results that showed that the expansion of the universe was accelerating, Peter Nugent and I would exchange a flurry of emails saying, we got the sign wrong. And it was actually an effect which would make the universe, a happy lambda equals 0 universe, and we would freak out for 2 weeks. And then I would say, but if we got it wrong, at least, that other team got it right, right? I mean, this is a cross-check. And Peter was like, I think we're all using the same numbers. So if there are any graduate students out there who want to check this out,
There may be a Nobel Prize in there for you, or they may take it away from these guys and give it to you. Thank you.
Peter Bernavich? No? Okay. Ron? Sorry.
So in 1996, I had an HST program that was approved through the TAC process, an exploratory program to try to find supernova type 1As by revisiting the Hubble Deep Field. Now, the only reason I mentioned that to start is that Bob Williams invited me into his office one day and said there was a director's discretionary proposal from Saul and the SCP, and Bob asked me if it was interfering with my program. Of course it wasn't, so I said there was no problem there. And then Bob went on to say that he thought it was very important for the field to foster the competition that was very well known in the community at that point between the High-z team and the SCP, and asked me if I had any thoughts on that. And I think I agreed with Bob that it was a good idea. I can imagine there was some consternation on the part of the SCP, because not only had Saul submitted the proposal and the High-z team had not, but the High-z team's initial response when Bob sort of offered the time was that they didn't really think it was essential. It turns out that, of course, HST has been very important for developing the science. There have now been over 2,000 orbits used by the two teams, almost all of which was allocated through the TAC process. But I think Bob Williams was very forward-looking and recognizing the importance of this, which ultimately brought the two teams to Stockholm and did the right thing in fostering that competition. I later was invited to join the High-z team, and then in 1997, the program I mentioned that I had on HST executed. And in early '98, we published an IAU telegram announcing the discovery of two supernovae, one of which was 97FF. It happened just by chance that Roger Thompson, the PI for the NICMOS instrument on HST, had a very long series of observations coming up over the next month. And we sent an email to Roger Thompson at the same time, telling him that we had found this supernova and asking if it was in the much smaller NICMOS field of view. And Roger, as many of you know, can be rather curt at times, and his reply was, "Your source is not in our field of view. I can delete your images unseen from my email. I have not attempted to decompress them." So I sort of scratched my head wondering how he knew the supernova was not in his field of view if he hadn't looked at my data. But anyway, I decided it best just to wait until the data became public. And when the PR image was released a few months later, it very obviously was in the field of view. And Peter Nugent did some modeling suggesting that there was a good chance that the light curves would be very interesting using the infrared and combining that with the optical data. Fortunately, Adam came along, and a couple of years later, very brilliantly put together the information in the NICMOS data with the optical data that Mark Phillips, Peter Nugent, and I had published, and published a paper that provided the first indication, looking far enough back in time, that we not only had seen evidence for the accelerating universe, but the earlier time when gravity was still winning out and the universe was decelerating. I think even more important, something that didn't get squeezed into the title of that paper, was that that single supernova was fairly influential at that point in ruling out types of false positives that could have torpedoed the results that came out in '98 and '99 from both of the teams. And I don't have time to go into the full story, but there were many levels of serendipity that came into getting anything out of my HST proposal in 97FM. Thank you.
Okay. Peter, then Andy. I guess that's what happened.
Well, it's not very well known that Brian organized the High-z team not as a hierarchy, but as a network with nodes in various places. And the idea was actually to have people work hard at a particular project and be first authors on those projects. So it worked out very well for me. It worked out very well for Adam, as it turns out. But the first paper on the data from our project was, if you want to put on that slide, was from the HST data. It was a search done at Hawaii with John Connery organizing that, and HST observations were coordinated with Ron Gilliland and Pete Chalice. And as you can see, the data from HST is spectacular. That's a Hawaii image, a 0.7 arc-second image compared to the HST image. And it was a pleasure to work on this. Harvard got the first node in this first paper, and well, we put it together with the help of a lot of people. But we wrote the paper, sent it out to the group in September of 1997, and got a lot of responses. It's one thing to do a search; it's another thing to write a paper. And Nick Zunsif, I wanted to point you out in particular. You sent a 49-10-page critique of the paper, which it's a four-page letter. So, but you know, Nick is the most careful astronomer I know and the best photometrist in the world. So he really helped that paper and made it what it was. And this paper allowed us really to get the cobwebs out, get our team thinking about papers, and I think it really smoothed the way for Adam's paper, which just was a few months later. It allowed me actually to go to the STS meeting in January of 1998. This was a special time for me. My father had just had a heart attack a few days before the meeting. It's Washington, D.C. My father lived in Maryland, so I was able to go visit him. My wife and I were able to go visit him every night of the meeting, and gee, the STS meeting had that very exciting press conference. The entire press of the United States was there, and I was able to make the front page of the New York Times, the Washington Post, bring him those front pages while he was in the hospital. So it was a really exciting, spectacular time for me, and of course, a few months later, well, we had a very nice result here. You might notice there's omega matter is minus 0.1 plus or minus 0.5. It was pointing in that direction. Of course, the error bars were a little too large. We only had 4 supernovae at the time, so Adam's paper with many more supernovae really narrowed those error bars, and well, that's what I had to say. Thank you.
And last in the session, Andy Fruchter.
Well, I first met Saul when we were both graduate students. I think it was probably 1988. So, yeah. And I was working with Joe Taylor at Princeton, and Saul was doing a bit of a tour, going around speaking to people, I think possibly about jobs, but he already had one. And we hit it off right away and became friends. And he told me that he decided he was going to stay at Berkeley, and he was going to measure the mass, the geometry of the universe. And I remember thinking, I don't think I told you this, Saul, but I remember thinking, Saul's either going to get a Nobel Prize or end up homeless under a bridge. Now I guess you could buy the bridge, and actually if you'd like to. And then I went out to Berkeley myself in the early 90s as a Hubble Fellow, but I didn't work on supernovae. Saul and I had some fantastic Asian meals together, but we didn't do a lot of supernova science. It wasn't until I went off to the Hubble Space Telescope, Space Telescope Science Institute, that about I guess 18 months, 2 years after I got there, Saul called me up and said he wanted to observe supernovae with type 1a supernovae with HST, and it seemed like a good idea because, as you saw from Peter's image, you gain a tremendous amount by going to the Hubble Space Telescope. Although its aperture is about 1/4 Zk, right? Its PSF is about 10 times smaller. Its point spread function is about 10 times smaller. And in addition, there's less background light. The atmosphere not only wiggles the image, it glows. And so you have those two things winning. And it's that latter effect, the fact that the atmosphere glows, that's going to make James Webb Space Telescope such a tremendous improvement over the ground. And so I thought this was a great idea, and we decided to do it. But I had a very different expectation, though, than, Adam describes and Saul describes. If you bring up the next slide, yeah. I had been paying attention to the observations less than the theorists. Well, I mean, this actually is a paper by theorists, so not all of them. You could listen to some of them, but you wouldn't have, because this paper was written by Jerry Ostraker and published in Nature, so I think most people didn't believe it. But Richard Ellis is nodding. But I had believed, you know, if you believed the observations in the mid-90s, you realized that you had a choice. You had a choice between an open universe with a low matter density and a non-flat universe, right? Which wasn't what you wanted if you wanted inflation or just like the idea of a flat universe. And you know, because you pass through you go from omega 1 to omega 0 very quickly, right? It's a very fast transition, and so we'd be in a very special time. But that's a sort of that sort of argument you can take or you can ignore. But if you looked at the data you found, this is a little blurry, unfortunately. I guess I got transferred into PowerPoint, yeah, right, it's a PDF. Anyway, but if you looked at it, you put in the various observations of age, what your constraints on age of the universe, on H0, and the matter density that we knew from clusters of galaxies, you found that you had very little choice if you wanted the universe flat, but then to believe that there was a cosmological constant. So when we found the cosmological constant, I wasn't terribly surprised. What I was surprised by was how so many people wouldn't believe it. And so it goes to show, I think, that, you know, another story about gamma ray bursts I won't go into about this, that theorists tend to believe their assumptions after some time, and the whole field tends to believe its assumptions are correct. And that when they find out that the assumptions are not supported by the data, they will fight very hard for those assumptions. But I'm very glad, Saul, that you overthrew those assumptions and we're not under a bridge.
Well, thank you for this panel, and I think for the last panel, before we still open up for questions, we have Gubar, Jacques, Tanri, and Hogan. Let's see, I'll start with Ariel first.
Actually say something about them. So, 20 years ago, I actually defended my thesis, almost exactly this day, I defended my thesis in particle physics in a group led by first Riess and Sven Holmgren here. I was searching for the Higgs particle, and I made a prediction that it would take at least 20 years before somebody would find a Higgs. And I think so far I've been correct. So I decided I had to do something else. And while I was at CERN, searching for the Higgs, I did find something. I found this gorgeous woman who actually was an astronomer. Not only was an astronomer, she was interested in supernovae, and she introduced me to other supernova people like Bruno Leibengut, in fact Brian Schmidt. So I eventually started getting interested in supernovae and got in touch with Gerson Goldhaber, which, as we heard, it was a fantastically inspiring person and invited me to come over to Berkeley to work on this project. I resigned an extremely well-paid job in Switzerland to do this, and can you imagine my surprise when I came there and I met Heidi, and the first thing she said is, well, I've been working with this for many years, you'll never find a supernova with this, I have never found a supernova. So I was like, my God, what have I done? And then I talked to Gerson again, he said, don't worry, it only takes one supernova. You find one supernova, you're done. I said, well, that doesn't sound so bad, So eventually, and after a lot of struggle, we did find this supernova, and I'm showing these pictures to show that, yes, I did have hair at some point. So we were extremely proud when we found our supernova, which has been shown here before, the one where I think Richard showed the spectrum of. So for a short while, we thought we were done, and then we realized, oh my God, the answer doesn't look anything like we expected, so probably we need more supernova to figure out what was going on. And then, chatting with Saul, we realized, well, I think it's mainly based on the things that were on the literature where Andy was saying that people were actually saying that could be a cosmological constant. We realized that maybe we can actually go ahead and measure both things, both weigh the universe and figure out whether Einstein was right or wrong. So Just quickly, so we realized that just because the cosmological constant is a constant, whereas the matter density actually increases as you go look in the past, we figured out that, well, we can actually do both. And at the time when we set this paper, I don't think we thought much about it. I don't think we would ever measure anything like that. We thought at most we get an upper limit. So I think we were both very, very surprised that actually ended up working, and I would say it pretty much worked exactly the way we were thinking. So, well, I'm of course extremely grateful to, well, all the people I mentioned, and I want to emphasize Gerson, who's not here with us, unfortunately, and was a fantastic host for all our parties and got us all working together in a very nice fashion. So, and thanks, Saul.
John Tonry, are you ready for the next? I think you're.
That's all right. I don't need any slides. So we've been hearing an awful lot about supernovae, but I'd like to circle back a little bit to what Nick and Andy alluded to. For me, this all started in 1991. My colleague up the stairs, Alan Guth, was absolutely certain that the universe was flat because he'd come up with this amazing model that satisfied and solved an awful lot of cosmological problems, but absolutely had to have a flat universe. And my next door colleague, Ed Birchinger, said, oh, no problems. I'm looking at motions of galaxies. I see enough matter in the universe to actually meet what you're doing, what you're requiring, Alan. It's all solved. But unfortunately also, my colleague Paul Schechter and I thought, no, this isn't right. But the thing that was most interesting to me was what is known as the H0 T0 thing. The T0 is just what's the age of the universe, and you can pretty much figure that out from the ages of the stars. And H0 is the expansion rate of the universe right now. So it's like having your trip computer in your car that's telling you it will be so many days or so many hours or so many minutes until your destination, except H0 works backwards. It's totally weird units, but it's telling you how long it was since the expansion, since the explosion of the universe, if things continued at exactly their present rate. And so those two numbers together, the ratio of those two numbers, actually is a very telling thing. If Ed were right and the universe were flat, then it had to be 2/3. But what we were actually measuring and what we were really pretty darn confident about was that it was 1 or maybe even a little bit bigger than 1. And this was actually quite an accurate measurement, although it wasn't well known, appreciated in the early 90s. So to me it was very obvious that either inflation was wrong or you had to have a cosmological constant. So then, when I learned about Mark Phillips actually taming these stupid supernovae, so instead of being junk explosions, they were actually useful explosions, I was completely excited. I said, wow, this can actually work. We can actually, instead of having this global measure of what the universe has been doing, total age and predicted age, extrapolated age, we can actually look backwards. And I thought that was just terrific, and I was very pleased to join the High-z team and do the work. But one thing I want to mention and remind us all about is, I mean, what could be weirder than dark energy? The universe is expanding. Well, I'll tell you what could be weirder. That the universe was born in a false vacuum, a metastable state. It went whoosh, expanded exponentially many, many, many orders of magnitude before somehow it changed and coasted now into the universe that we've got. And I have to say that my hat is really off to Alan Guth. I hope to see him here someday soon.
So John will speak next.
Okay, I wanted to give you a little bit of the view of one of the worker bees, as we called them on the High-z team. So I was a second-year graduate student, or actually really a first-year graduate student when I started working on the High-z team. So you can go ahead. Peter Garnrich and Adam have talked a little bit about the way we had handed off these supernovae, that different people were assigned to lead different sets of supernovae. And so for the set of 10 that was in Adam's paper that's being celebrated for our team here, Adam was sort of the taskmaster for that, and so he had farmed out the analysis of the supernovae to a bunch of different people. And you can see this email from October 1997. To me, Peter Garnovich, Brian Schmidt, Alan Dierks, Pete Chalice, David Riess, all members of the High-z team. And so we had established some sort of, I think Adam probably established by fiat, some date at which we had to turn in the photometry so he could take the numbers and go ahead and write the paper. By the way, Adam is fastest from going from data to paper of anyone I know, and it's a really great skill that I have absolutely not been able to learn at all. So these are some managing team lessons I learned from Adam in this process. And remember, this is receiving these emails as a second-year graduate student. So it says, wow, can't believe it's almost here, the deadline, emphasis on dead. Notice the subtle threat there. So that's also, where learning about team management, threatening your workers seems to work. Only 2 days left to turn in your completed relative photometry. Well, the relative supernova photometry was using software mostly written by Brian, and it wasn't the most let's say documented. That's well documented software out there, and so it was taking us a while, and it was taking me a while too. This is relatively new, and so in fact I missed the deadline, and I didn't get it in. I knew Adam was going to be really, really mad. So if you go to the next email, so the next email, which was 3 days later. He sent it to the same people. He said, "Dear hard workers, thanks to all who sent in their light cards yesterday. I received everyone's except for one person." Uh-oh, that's a bad feeling as a second-year grad student when you read that. You know who you are. So at least he was nice enough not to single me out by name. And when they send theirs in, I'll have them all, so you know who you are, me. Get moving. Thanks again to all. So this message really had me shaking in my boots. And I went to find Peter Garnovich or Pete Chalice, and I couldn't find them, and so I was like, okay, I just need to get this done. And I think I spent about the next 36 hours straight working on the data. And I finally did get it in to Adam, maybe a day or two later. And then I finally saw Pete or Peter in the hallway, and I said, I was the one holding everything up, and they looked at me, blinking, being like, didn't you realize that was a joke? No one got their data in. So thank you for teaching me about that. I want to spend the last 30 seconds on the final slide. So actually in 1998, which was a really exciting time, the High-z team actually had 4 papers, and 2 of them that were led by Peter Garnovich, and I wanted to show this one, where this last paper, which was in December, most of it focused on constraining the cosmic equation of state. We called it alpha then, and instead of W, we were told by smart people that it could never be less than -1, so we didn't include that on the plots. But one of the things that I did on that paper, and which I want to mention, is already at that time on the lower left, the CMB data were kind of showing, even mostly from the ground, some evidence for that first Doppler peak. And you could turn that into a PDF on the cosmological parameters, and that's what I did, and combining it with the supernova data. On the right was sort of the first plot combining those data and showing that concordance model, which is really zeroing in on a flat universe that's dominated by lambda. So even as early as 1998, we had hints that seemed to be the right answer. Thanks.
And symbolically, I think I put Craig last on the program, partly to get us thinking a little bit into the future, because he's acting as in our role as our theorist as well.
Well, this has just been fantastic. I mean, this is it's been a breathtaking session. It's been a breathtaking week. So this was a great discovery. It deserves a Nobel Prize. Thank you, everybody, for making this great discovery. But of course, it's only half finished. I mean, the great discovery about the universe is a property of the universe. The job's only half done. We don't understand why the universe is accelerating at all. And some people have mentioned earlier this famous 120 orders of magnitude problem. That is a problem that we're facing. It's the square of the ratio of the Hubble length to the Planck length, which is about 10 to the 120. That's the prediction, according to naive physical theory, about what the value of the cosmological constant should be. That's how far off the theory is. And so why did this get the Nobel Prize? It's not just because it's interesting astronomy and wonderful work. It's because it's about really profound physics. It's about the behavior of matter, energy, space, and time at a level that we don't understand at all. We have, on the one hand, we have all the quantum mechanics. On the other hand, we have space-time. These, we don't understand how they fit together at all. They're completely incremental types of mathematics. So what we're really talking about here is the nature of physical space, of where does space come from? It's not something that just exists. It has to be something at some level that's made of quantum mechanics, like all the matter and energy is, and we don't understand how that works. So, so the question is, what's next? What do we do next? And so astronomers know what to do. They're going to go out and get better data. That's what astronomers do. There is something called the Dark Energy Survey that's about to start doing a Dark Energy Survey, and many plans are being laid to study this same behavior much more carefully and study the details of how the matter and energy behave with the space and time. But there's another interesting side to this is, I mean, remember it's the ratio of the largest scale to the smallest scale squared gives you 120 orders of magnitude. Turning this in on itself, we can ask ourselves, are there experiments that we can do to peer into inner space? Inflation is one example of that. It could be that the reason why we don't understand it is that we're using much too naive a theory of space-time. Many theorists believe this. There are many suggestions from gravitational physics and black hole physics that there are other suggestions of mysterious behaviors like the evaporations of black holes, the holographic behavior, the fact that maybe all of physics can fit on two-dimensional surfaces like it does on the event horizon of a black hole. So some ideas about explaining dark energy are based on introducing new fields, new types of quantum mechanical fields, so quintessence fields and things like that. Others are just putting in a number, like the cosmological constant. But you could also ask, well, maybe our understanding of fields, of particles and fields, is too naive. And the way that you quantize fields on a classical space-time background is already too sophisticated. It's taking too much for granted. And so physicists are starting to think about going down to the most primitive level. I mean, so this is something that we all learn about when we're little kids. We learn about space. We learn about positions in space. It seems like a perfectly obvious thing. And maybe that's too obvious. Maybe positions in space are already something that you have to build a new theory for. So, and there are hints of this already. If you think about some other areas of physics, mysterious, spooky action at a distance is something that has been studied for decades in quantum mechanics. Still isn't understood. Still seems spooky. That word still seems appropriate. What if space-time has some of those properties? What if it really is a quantum mechanical object? So there is no standard model for this. There's not even a real school of thought about this. There's a wide-ranging literature in physics about ideas for how to treat it. What I'm personally most excited about, and this is what I just say, a plug. What I'm personally most excited about is, can we actually do experiments to shed some light on that problem? If you think back 100 years ago, when quantum mechanics was being invented, quantum mechanics never would have been invented unless it was forced to exist by data. The Fraunhofer lines and the energy levels of hydrogen were so weird, you had to invent new kinds of mathematical algebras to explain them. It forced people into this very strange theory. This discovery, dark energy, is doing the same thing for us now. It's forcing us to think empty space has a behavior to it. We don't know how to explain it, but there it is. And there might be experiments that we can do in the lab where we can study the quantum mechanics of space-time. And we're building one of those at Fermilab now. I'll tell you about it in a year or so.
Let's thank all the panelists so far who have spoken. So one round of applause for everybody who's spoken, and now let's do questions. So I think we've saved enough time for questions. And from the audience, and also I think that since we didn't have time for all members of the groups to speak, they may actually want to raise their hand if they have an interesting extra little memory or item that they want to throw in as well. We'll let to moderate. Should we just
raise your hand if you have a question. Do not be shy.
First.
Okay, I'm a student here. I have a strange question, maybe. I don't know. Maybe it's easy, maybe it's hard. The idea is, it's a two-part question. The first part is the universe isotropic, homogeneous, and infinite? And if it is, if you choose any place in the universe at all, and you say how much mass is in that way, and how much mass is that way, wouldn't they balance each other out? Wouldn't gravity in general balance each other out, and therefore not collapse the universe?
So, should we ask for a team member who wants to answer? Right? All right, so
Well, we can.
we haven't thought about this part. How do we do a round robin answer?
He seems to be I'll start out at least and say about homogeneous and isotropic. You know, it starts out as an assumption that we make, the cosmological principle, and then we look out and we test it, and it looks pretty good. We look at redshift surveys, which is probably one of the best ways. We look at the cosmic microwave background, and so we go out to a certain scale, and we've gone well beyond that scale at this point, and the universe looks that way. Now, we can only see out to the horizon, and it's possible that once you get beyond the horizon, it completely changes. Now, that would be perverse. The power spectrum of fluctuations looks like it's decayed away, so it would be crazy, it would be, you know, a giant conspiracy, but we really can't say beyond the horizon. And infinite, yes, it looks, I mean, the most naive interpretation of the data at this point suggests that it may be, and as strange as it sounds, something infinite can continue to grow in size.
Yeah, when he says infinite, it's much, much bigger than what we can see. That we would guess it goes way beyond the horizon. And the way the gravity works instead is you have to use Einstein's equations of general relativity, and it naturally tells you how space behaves over time. And we need something like dark energy to make it speed up. That is, energy tied to space, rather than just atoms. And that's a natural consequence of solving Einstein's equations of general relativity.
Okay, next question.
It's all right to ask philosophical questions or team questions about things that happen. Good.
Okay, let me ask a question. So, Adam, Brian, congratulations. Is there any chance in the next few years you could make our lives infinitely easier and not have, I've sat through 5 TACs now where great proposals come for dark energy to the TAC, and each of you in turn win roughly 100, 200 orbits, but only one of you. And the TAC always says, do I really have to toss a coin? Can't you really get these guys to work together? We're in the last 5 years of Hubble, and you know, when one of you gets time, Saul, you call me, yes. When another gets time, Adam, yeah, my assistant says, Adam's here to see you. And I know that you like the marketplace, but within the last 5 years, are there programs that need more than 100 orbits of Hubble time? If you had 1,000 orbits of Hubble time, what would you do for the dark energy problem? Because you've got one shot. Nothing else is going to replace Hubble for a while. It's probably going to be finished by about 2017, 2018. So the question I have for the teams is, if you were to propose a very large Hubble proposal in this area, is there one? And if there isn't, I'm very happy to keep on going and have the TACs and have you guys call me and have Adam come into my office or have Brian call me. But in the other world, now you all 3 of you have crowns. Is there a possibility of a coherent dark energy program?
So just as a background, for the people in the audience, that is the Director of Space and Hubble. So Saul, why don't you start?
It's always dangerous to pass the mic the first time, right? Because no, I mean, I think that actually I think it's very possible, and we have in the past done work together on some proposals before, and I think the tricky part is always this one of just trying to figure out, where do we benefit by having 2 teams, doing things their own ways, and when can we say, look, let's do these things together. And I'm betting that on this kind of round, when we're talking about very large numbers of orbits, that puts us back in the mode as we were at the time when we were working together on things. So I'm guessing that we'll with that kind of very generous invitation, we happen to have a proposal here, if you wouldn't mind. So, exactly. So we will. I'm sure we'll be talking about this next 3 months.
Any other questions?
Come on.
Nick.
I have one question. This is maybe my own cynicism, but so far as we've done this project, astronomers look at this project as we're measuring a number. Physicists look at it as this is big stuff. To us, I mean, when I look at the equation of general relativity, it's g plus lambda, and we're solving for two numbers, and we already know what g is. The thing is that with all the hard work we've done, w is -1. And it seems to me extremely unlikely, as an astronomer, that if we reduce the error bars, it's going to change from w of -1, and that we would live in such an unusual epoch right now that w prime would be anything from 0. So why are we wasting our time trying to measure w prime at this point? Why are we not spending our resources measuring w, which is actually a lot easier than w prime?
I guess I'll say one thing.
Could you translate?
Sure. So Nick is talking about the way that we describe dark energy, and in particular the two parameters that we tend to focus on the most, the equation of state, the ratio of the pressure to the energy density, and does that change with redshift? I'm going to take a slightly oblique answer, which is people generally say, why bother at all, really, because it looks close to -1, and so it's probably, I should say, if it is a cosmological constant, if it's vacuum energy, then W will be -1 and W prime will be 0. I guess my answer is that I was burned a long time ago by thinking that the universe was decelerating and that there wasn't anything that interesting we could find. So I think anytime that we could think of a sensible way to make a significant improvement and it's economical in the measurement, we should do that. But I'm going to let one of these guys say something about the W naught versus W prime.
Well, I'm going to be contrarian and say that I never ever think of that. Right now we have a perfectly good model of the universe, which is the cosmological constant, forget W, and so that makes a very nice prediction. It's the only model we have that makes a prediction. It's the only model we can test against right now that's stood the test of time. So I simply want to test that model, and so I test against that. And if we ever find a problem in that, I am going to worry about whether or not I can describe it as some function. So I'm really just thinking you just test Einstein's basic idea. But I think we need a currency to describe how good experiments are doing that. And the W and the W prime description is essentially, you know, your euros to describe how my experiment's better than yours.
And I think I agree with both these points, and may I just add one or two extra ones. One of them is, well, I think that when one tries to figure out what is the simplest picture that we currently have, in some sense the cosmological constant is a very simple picture that we, there was already a lambda in Einstein's equation that he threw out, but we're bringing back. And so that sounds like an easy way to go. On the other hand, there's another way to think about what's a simple picture, and you might say, well, we have at this point very strong evidence for a early, as you were hearing earlier, an early epoch, just the first fractions of a second in which the universe went through a tremendous acceleration. In that particular case, the acceleration then switched over, it decayed away, whatever was powering that acceleration decayed away, and we ended up in this universe that was coasting for, apparently. So you might say, well, if you ask what is the simplest possible explanation for the current acceleration, you might say it would be something that was parallel to that, and that whatever it is that we're currently experiencing will decay away as well. So it's not clear, when you hunt for what's the simplest explanation. Now there are arguments against, both of these alternatives from the point of view of what is simple for a theorist, but it's not always clear where the simplest explanation lies. And so that leads me to say we should be looking carefully. And then the other point I would put in is that in some sense I think we're still at a reasonably early stage of cosmology theory and understanding of cosmology. And that as we've gotten dramatic steps forward in new sets of data, our story, although it's pretty simple, has changed each time. And so, as Adam mentioned, when we were making these particular measurements, there were many people who told us that they already knew what the answer was. They were glad we were doing it, but they already knew what the answer was going to be. And I think that you want to keep, if you have the opportunity to develop a whole next generation experiment in a field that's so new as cosmology, you should do it. And ideally, you should do it until you start getting answers that don't give you a surprise. And we haven't yet, I don't think, reached that sense that we've asymptoted out in our efforts. So for those who are still looking for projects to work on here, I'm still an optimist that we don't yet have the full cosmology story down pat at this stage.
And the final question to John Torrey.
Well, I think I would actually like to pick up what Nick said and just be a little bit obnoxious and say it's also a question of efficiency. I mean, this is what Matt is talking about. Personally, I would bet it's as likely that the universe has an anisotropic expansion as it is that we don't have a cosmological constant. And so if we do not have the imagination to do better, and we've got infinite resources, we might as well spend it testing for omega naught different than -1 or omega prime different from 0. But I would really like to encourage us all to think hard about efficient uses of resources and what's the really creative things that we can do next. I'm actually thinking this is a little bit of a dead subject. And I'm looking forward to the next bright idea.
Good country.
So before we close this and let everybody give their hands of applause, I think we should invite everybody from both teams down here on stage, please. So, now is the time to give a hand of applause. Thank you everybody for this.